Hello and welcome to Rebelway. My name is Savage Jalasi, and today we're going to go over the creation of this awesome face splash effects as well as rendering using Karma and Material X. It's going to be a two-part tutorial. The first part, I'm going to go over the shading and rendering and explain how the UV technique works. And the second part is going to be taught by my colleague Andrew Sutherland, who's going to explain the simulation process in depth. Thank you so much, and let's get started. All right, so let's take a closer look at this. So what we have here is a flip sim emitting fluid in the first few frames, and then that fluid is then dropped onto this face, and with the retiming of the solver, we can get this nice slow motion effect. And there's also viscosity and all the tension features to get the nice tendrils and stuff. And so with flip, or with any tricky sims like this, it's hard to get a nice UV coordinate that is that flows along the mesh nicely. And so we have a simple trick for this that should work in even more complex scenarios. And this is the flip sim. It's coming in here, and we turned off receding. So we have we turned off receding, and also all the points get emitted in the first few frames, which should be fine, but the point count doesn't change that much throughout the sim. And the other thing is we have an ID attribute. So that's very, very important for this technique to work. And when you think about it, I mean, there's a few frames that we could use where we want the UV coordinate or the UV textures to be perfect. And let's say at frame 30, we like everything about the sim, and we want to initialize our UV coordinate in that frame. So here we have, I'm using two different frames to create two different UV coordinate that I can use. And I'm gonna go with this one. So this is the one I used, I believe. So it's frame 30. And the idea is to create a UV coordinate. So we just place a planar projection here and apply a UV coordinate on that. And if I use a UV quick shade and visualize this, I don't think it's going to work on points. Yeah, it's not going to work on points, but if we create a UV coordinate at this position and then mesh the surface and transfer the UV coordinate to the mesh, we should be able to get something like this. Second. So we should be able to get something like this. So that's our UV coordinate being displayed with a texture on the mesh. And because we have an ID attribute, I can use this frame hold here and copy this UV coordinate back onto the flip sim. So if I go backward to frame 20, let's say, I'm going to basically reverse the animation and still inherit the frame 30 UV coordinate. And you can see how it's staying, it's working backwards, basically. So at frame 30, it's going to be perfect, but everywhere else it's going to be stretched. And because we used a frame somewhat in the middle, we should be able to get nice stretchy effect throughout the entire sim. And the idea of using two different frames is that if the first one is too stretched and you are using a different camera, you have an opportunity to pick a different one. So the one I'm interested in is copied to the mesh by respecting the ID attributes. So from the point to the flip sim, from frame 30 to the flip sim, and then when we mesh the data, we keep that information. So here I'm just visualizing that. We also have an a color attribute on the mesh that's generated based on a noise from the rest attribute. So because we emit all these points at the same time, we give them a rest attribute, and that is being used to drive this. So I'll use two things to generate textures. I use this map here, which I'm going to remap, and also the UV coordinate. So let's go to the stage. I'm not going to rebuild this from scratch because it's fairly simple. And let's make sure we're looking through the right camera. So here I'm importing the flip mesh. And this is the camera. I created a couple of cameras. And here I have a sky using a default HDRI texture that comes with Houdini. I have an area light from the bottom, and a fill, and then a key light from the top to create the majority of the lighting here. And then the shader is just a material X, which I'm going to explain in the next video. So I'll continue there in a bit. All right, so let's take a look at the shader. So what I have here is a standard material X. So you can just create a standard surface, and this is the default. And what I've done is I imported the color attribute. So we use a material X geometry color. So there's a node, and it's going to look up the CD attribute right away. But because of the naming conventions, we don't have to worry about that. It's just gonna, if you have a CD attribute, it's gonna work. You don't need to worry about anything there. And I'm plugging that through a color correct to increase the gamma. And let's say I'm plugging that here straight into this ramp. I'll explain what this is in a bit. And I'm running that through a remap to just get more details into this black and white map. And then this will go into another one to give it random colors, or actually driven from this map. And then I'm using 3 variations of that, one for the diffuse, one for the transmission color, and one for the subsurface color. And each time I'm just changing the hue, the saturation, the gamma, and the saturation again, just to create variation in the layers. Now, the second part is adding or generating a noise based on the UV coordinate. So here I'm importing the UV coordinate that we created in SOPs through a geometry property value. So I'm going to create that material X geometry property value, and you can type in whatever attribute you want. So in this case, I'm using vector2, and I'm importing the UV. And I'm plugging that into a unified noise 2D, and this is a material X node. And then that goes into the bump, which is connected through the normal. And I'm also adding that to the colors. So I'm adding my noise to the color. So I have more variation in my texture generation. And that's pretty much it. I have some a transmission here, so 0.7. I have some sheen to create some sort of Fresnel or velvety look, and then some subsurface with a very small radius to get the subsurface effect. I'm going to try to render this, so let me switch to the camera. Let's go to the camera. And this should work perfectly fine with the Karma XPU as well. So I don't have nice GPU, so I use CPU for now. I'm going to switch to Karma CPU. And there we go. We have our shader. Now we'll supply this file with the geometry of this still frame, maybe frame 60. And you guys should be able to replicate this effect if you wanted to render this with XPU or explore anything with the renderer, honestly. All right, thank you for watching, and talk to you soon. Bye-bye.
Hello everyone, and welcome to Rebel Way. My name is Andrew Sutherland, and today we're going to be creating the small-scale fluid simulation. I'm going to be covering the simulation part, and then I'm going to hand over to Saber Jalasi, who's going to cover the rendering and shading of the scene. So, diving into Houdini, and you can see we've got a geo node, and in here we've got some geometry. So, the thing with, small-scale simulations is that we're going to have to scale them up. You hear a lot of effects artists say always simulate at the real-world scale, but in the case of small-scale simulations, we do need to scale them up. So, in this case, we're scaling up 7.5 7.5. So if we put down Tommy as a reference, you can see this is real world scale, and let's just transform Tommy down, and we can clip his head, something like that. And then, you know, compared to that, it's almost 10 times the size. In fact, let's just put down transform and see how big this actually is. We put a value of 10 here. So not quite, yeah, it is about 7.75 times the real world scale. And that's the scale that we're using for the scene. So we're just deleting the selection here, we're transforming this back, and then we're clipping it. And then you can see we've got a hole underneath, so we're going to put down a polyfill, and that's going to make sure that we've got a watertight mesh. And from there, we're going to prepare this for our simulation. So we can just put down a null. And this will be our geometry collision. And then we need to make a VDB version. VDB from polygons. We can maybe increase this to 5. Out collision VDB. Cool, so that's what we need for our collisions. And then next we're going to put down a sphere, and this is going to be to source our points. And what we're going to do is we're going to animate the scale of this sphere, and we can do that using a fit in our uniform scale. So we're going to expression for fit, and then we're going to say $FF, so the frames, and we're going to fit it between 2. I've got this expression here, and what this is going to do, this is going to scale our sphere. So we're going to use the frames 2 and 15. So on frame 2, we're going to have a value of 0.95, and then on frame 15, we're going to have a value of 0.02. So as you can see, it scales down like that. Cool. We're just going to position this above our head, so let's template our face, and let's raise this. Let's make this radius 1 actually. Yeah, something like that. Set this to polygon, frequency of 20. And from there we can put down a flip source. For now, let's just increase this value. And I don't want to look at this as a VDB, I want to see the point version. So I'm going to put down a primitive node. And if we come under volumes, we can say adjust visualization and then set this to invisible. And you notice we can't see our points. So we actually need to come over here and we need to change this off to something and then change it back. And now we can see we're getting some of our points here. Let's make our point separation a lot smaller. So now we've got a lot of points. Click on oversampling, type in 90. And let's tick off this shell thickness. So that should be a better representation of our sphere. Here with this thickness on is going to make things thicker. We don't want that, so just like that. And now we have our points. And in our final scene, we had actually a few of these, about 5 of these sources placed in front of the face. But just in order to get, we'll share the final project so you can take a look at that. But to get something quickly, I'm just going to put down a sphere. Something like this, and let's make it flat like this. Move it up above. we can say VDB from polygons. I'm just going to make a density version of this. I'm going to make it a fog, and then I'm going to scatter. I'm just going to scatter 5 points, something like that, and then I can say copy 2 points. Let's maybe move this to the transform here so we can delete this later. Something like that. And we can say attribute randomize. And we're just going to randomize the P scale. And it's fit the value between, and we can let's try something like that for now. This is a little bit in the head, so we can also transform it up. Yeah, something like that. Next is put down a wrangle, an attribute wrangle, and let's set some initial attributes. I think Saber is using this attribute for some of the shading, but I'm going to include it here, but it doesn't affect the simulation. So I'm just going to include it for now, and if this is in fact used, then Saber will cover this. But what we do need is we need a temperature, because we're going to use viscosity. So let's, if it's a float value, so at temperature, I'm going to say equal to 1. And we're going to set a rest for the position. Cool. So from there, let's use an attribute VOP. And let's create a noise for our temperature. So we can say turbulent noise. Let's fit that. And let's put into color for now. Give this a frequency of 20 so we can scale things down a bit. Cool. Make an amplitude of 6. Turbulence 2. And let's expose this offset. So this is going to be our breakup in our temperature. And we're going to so we don't want to export it as color. Let's put down a bind export. And we can say temperature. It's a float field, and export that. Set our range. So now if we take a look at our geometry spreadsheet and we come here, I'm just going to say delete channels, and I'm going to set some animation on our offset here, 0.2. And you can see that this noise is moving, and that's coming from that offset animation. Pressing D on my keyboard, I'm just going to change the background to dark. And the next thing we're going to want to do is we want to give these points some velocity. So if we take on point trails, you can see we don't have any velocity currently. But if we put down another attribute VOP, and this one is for our temperature, so we can say, call this set temp, and this one we can call set V. Cool. And let's do the same thing pretty much. We're going to put down a turbulent noise. Take the position, put that into there. We're going to come to our offset, promote parameter, and export this as V. So now you can see we've got some velocities. So let's increase the scale so we've got some more variation. Like 25, 25, amplitude of 4, turbulence of 2, and I think we need to make this a 3D noise. Make this sparse convolution. That's better. So now we have velocities traveling in all directions, and like we did before, let's give this an offset, and that just means that this is going to change. And that's about it for our source. So we're just going to put down a null, and we can call this out source, and we can feed this into our flip simulation. So we have our source and we've got our collisions. And if you're a power guy, you might just be tempted to drop down a network and put down a flip object, a flip solver, and a volume source, and put together your little simulation. But with flip, you run the risk of just crashing your scene. So let's just save for now. Save the file. But to avoid making a mistake, I'm just going to come over to this particle fluids, and I'm going to click on this flip fluid object. I'm going to click here, click on my viewport, and click enter. And you can see it's built this little network for us. And I'm just going to copy this. I'm going to delete these. I'm going to dive back inside, put down a DOP network, dive inside, and then let's paste that little setup quick. Cool. We want to link this particle separation, so let's go copy parameter, and let's paste it on our flip source like that. We want to make sure our container is not gigantic. As you can see, it's huge. So let's go to volume source here, and then let's set this to 3 by 3 by 3. So now we have something a bit more reasonable. And you can see we've just got those points. So what we need is a volume source. Plug this in here. Let's initialize this. Let's just click on collision first, and then change this to flip source. And we can take our out source, paste that there. You can see out source. Cool. And let's make the activation. So we only want to emit from these points for the first 15 frames. So we can just multiply this by this function. Let's say $frame. So if the frames are less than 15, that way we'll see we'll have a value of 1, and then after frame 15 it's going to multiply down to 0. Cool. Perfect. Save again. Cool. So we can even make this smaller again, although our splash is going to splash upwards. That should be fine for now. Our gravity on our final scene was actually set to 4, and we were messing with the time scale, so I'll show that in a minute. Cool, and we're going to want to set up some collisions. So let's put down a static object, feed this in, let's swap these around because we want the collisions to go in first and then the solver. Coming over to collisions, and set this to volume sample. Let's set this by size, and let's take a look. Okay, copy that parameter. Let's take our subpath, and this is our collision. That's our our geo version, and then we're going to need our VDB version. This one. Cool. So in theory, we should have some collisions. Let's increase our resolution a bit. Let's go 0.5, sorry, 0.5. Let's raise our source. Cool. And on our substeps, let's use a fit. So basically what we're going to do is we're going to use this to animate our substeps. So we're going to fit from frame 10 to 15. So we're going to use the animation period is going to start from 10 to 15, and we're going to map the value before 10 to 3 and at frame 15 to 1. Let's close that cap. So as you can see now, if we toggle this on, it's going to be 3 until frame 10, and then it's going to come down to 1 by frame 15. And we can just copy this, and we can do that for the max substeps, paste that here, but on this one we can increase this to 5 and to 3, and then we want to weight our condition basically, so it's going to use this to decide whether it's going to use 3 or 1 substep or 5 and 3, and so we're just weighting it more towards more substeps. Let's save again. Let's call this V. Okay. And in the final scene, we actually also had an animation on our timescale. It was slightly modified, so I'm just going to copy it from the previous scene, because it's basically, it was this, and then we multiplied it with another version. And so as you can see now, you can see our timescale. So now we have this slow motion effect. Cool. So at this point, I think we can afford to increase our particles. Let's try this. Okay, so I've just had a crash, so let's be a little bit more careful. And let's go up to our flip source and our particle separation needs to be 2 times the amount of our flip sim. So let's see what this is. Let's take a look at our points times by 2. Okay, should be good. That's not many points at all. And our flip sim, I know that our final settings are that 0.5, but for now we're going to multiply it by 2.5 so that we are safe. And perhaps we can even make this domain a bit smaller. So let's come under volume limits. And we can, yeah, let's make this a lot smaller for now. Make this smaller even again. Cool, so this is working and it's playing back really quick when we need to tick on this so it plays back at the correct time. And you can see our sim is pretty stable with these settings. In fact, the entire simulation has been cached in RAM here. But, you know, I think what we should do is we should actually just cache this out to disk. Okay, so let's dive back outside here and let's put down a DOP import fields, and we're going to want this DOP network, and we're going to want this flip object. So let's copy this and let's paste that in there. And let's make this an absolute path. So, and under preset, let's tick on flip fluids, and we don't need the velocity, we just need the geometry and the surface. Cool. Next, what I want to do is create some visualization. So let's just put down an attribute VOP, dive inside, and let's compute the length of the velocity and plug that into the color, and let's fit it and plug it into a ramp. Set this value to 5, maybe in 6, and we can set this to white water. Cool. Let's make this a bit darker. Next up, we're going to put down a null, and we're going to call this toCache. And the main reason I have this null here is for my wedging setup. I created a wedging setup that I will show at the end of this tutorial, and this is we need a null called toCache for that setup to work. And let's put down a file cache. I like to mark these red, so when I open up a file I can just navigate to all the red nodes and cache them. Let's say explicit. Let's call this splash sim, and let's change our frame range to 180. Save once again. Okay, so I've just come over to this button over here, and I've run a flipbook, as you can see here, and this is our result. But how do we get from this to our final result like this? And as you can see, I've printed out all our settings on here, and I think the best thing to do when learning anything in Houdini and learning about the parameters and what the values do is to run wedges. So I'm going to just quickly show you how to set that up. And the first thing that we're going to need to do is we're going to need to install FFmpeg. So if you just Google FFmpeg and you click on download FFmpeg, you can come here and download for Windows. And so coming over to these builds, let's come down to here, version 6 essential builds. So as you can see, we're downloading this. Just wait for this to finish downloading. So I've downloaded this FFmpeg essentials build, and you can see inside here we have a bunch of files. And what I want to do is I want to install this on my computer. And so I'm going to create a folder in my C drive called Rebelway, Tools, FFmpeg, and then we can just drag and drop these files. You can see I've already installed it, but you just drag these here. So you now have that. And what we want to do is we want to add a path to this bin folder in our environment variables. So in order to do that, we need to come here and just type control panel. We're going to go to system and security. We're going to come here to system, and we're going to scroll down to advanced system settings. And then here we've got environment variables. And you can see here I've already created a path. So you can just do this by saying new, and we're going to type in the path here. So let's just take a look at how I've done that. So you want to call it just path, and then link C drive, Rebelway, tools, FFmpeg, and then that bin folder. And this is just going to allow us to write FFmpeg when we're executing some code, and it's going to execute that program. So, with that done, we can come over to our Houdini launcher, and let's go to launch command line tools, and we can just type ffmpeg, and you can see we have our ffmpeg installed. Cool. Okay, now that we have ffmpeg installed, we're going to add some information to our screen. So we're just going to create a camera called camera 1, and you can move around your camera by selecting this here and coming over to the camera button and moving like so. And then here we just bring down another geometry node. And if you dive inside, we can ignore this for now, but you can see we've got a font node. And let's just do this again. Your font. It's actually, for now, let's just start from scratch. So let's put down a geo. Let's call this info. Come over to font. And you can see this already is giving us our frame number. And if we say $hip name, we're also going to call our name of our file. So let's give us some space here. Let's put down a color node. Let's make this yellow because that's going to be easiest to see. And let's frame up and put this in place. Something like that. And then we can come onto this info node and we can say keep position when parenting, and then let's parent this to our camera. And now when we move our camera around, that font is going to stick in place. So we can come back and reframe our sim like that. And then of course we can just add more info, which is exactly like I've done here. So let me just save this as a version. Let's go back. Cool. So here I've just got more information, and this is information regarding our sim. As you can see, these are not quite linked properly, and that's because we need to call that geo flip sim. So let's come over to here and let's rename this flip sim. As you can see, we now got some more information, and just this flip object is not showing up. And the reason that's not showing up is that we need to, this is called dot network 1, and this is called flip object 1. So if we come over to our particle separation, we could just say copy parameter, come back to our info, and I like to make a separate font node here just so that I can say paste relative reference, and you can see that here. And let's come over to that info and let's see why that's not working. So our particle separation is here, so we need to replace this. And see, this was called flip object 1. So we can just take this and we can fix this here. Cool. So now it seems that we've got all the information that we're going to need to run simulations. We do add a microsolver later, so that is going to be this. But for now, let's not worry about it. And let's jump to our out context. I'm just going to enable this. And what this is going to do is this is going to write our simulation to disk. And as you can see, we're reading in this to cache. So if we come over to our flip sim, let's just label this red, dive inside, and you can see we've got this node to cache. So it's going to pull the information from this dot import fields. It's going to apply our visualizer, and it's not actually summing correctly because I've turned this cache off for now. So you can see we're pulling that data in, we're visualizing it, and then we've got this null. And then here, we've got our cache, and let's make note of where this is saving to. Because we're going to copy this, and we're going to make sure that we're paste that in there. So that's reading that. And then this out path is the same out path as here. So it's going to the same location. So whether you cache from here or whether you cache from here, it's going to be the same location. And then what this does, this just ensures that this caches, and then we move on to the next step, which here is going to be running our flipbooks. And in my case, I have aces installed. So I'm navigating towards, I've installed aces in my documents. So you can see, I go into documents, I come into my open color IO, and I go to aces, and I go to baked LUTs, Houdini, and then I select this sRGB for Houdini. If you don't have aces installed, you can just come over to none, or you can say LUT and gamma, and just make sure you have 2.2 here, and just leave that blank. That's close enough. But I recommend you have aces, and you use this display LUT. That just means that your color information in your flipbooks is going to be, as close to your viewport as possible. Again, this batch is just going to make sure that this process finishes before moving on to the next step, and then we're going to run our FFmpeg process. So this code here is going to ensure that we're going to run the sim. So we're going to cache this out. So here, this is our flipbook frames. This is going here, and we need the exact same path in our input here. So we need to read that in and then save this out as our MP4. And I find I often get a lot of issues if I change these locations. So just to be safe, I suggest saving your MP4 on the same folder as your frames, just to avoid any complications. And I know this is confusing by just saying render current frame. Don't worry about that. It's reading our frames in here. So if we come over to the very end here now and we just click on render, you can see we're writing this to disk. This is going to write our sim. I already had it cached, but we're going to just write over this. And then once that's done, we're going to generate our preview. As you can see, that's happening here. And we've actually got a problem at the moment, but don't worry about that for now. And once this has generated, it's going to generate our MP4. And you can see it's generated our MP4 here. Cool. As you can see, it hasn't cached our simulation correctly. So let's just take a look at why is that happening. And I think it's because this is caching twice. So what I like to do is just come over here and turn caching off when I run our flipbook. So let's do that again. Let's come over. Let's delete this. As you can see, this is now working correctly. Cool. So now we have our flipbook. Okay, so now that we have a setup that can generate our flipbooks, we're going to run a whole bunch so we can iterate over these values. So this particle separation that is coming from here, I'm actually just going to pin this so we can take a look. We can see our particle separation is here, our particle radius scale is here, and our grid scale is here. So for now, we want to run our simulations at a low resolution. So this is our final resolution, and I'm just multiplying that by 2.5 so that we could iterate quickly. Also, our grid scale, our final resolution was 1.75. But like I said, we want to run over this quickly, so a value of 2 for our wedges, and that's just going to be, it's going to help. It's going to prevent crashes, and we can iterate over our simulation, and then at the very end we can increase these until until we get a crash or we're happy with our result. So next up, we just want to run through all our main settings, and these are our main settings that are going to affect our simulation in this case. And you want, if you're not sure what something does, you can just run a wedge. So run a wedge with, for instance, the time scale 0.2. You can change that to 0.5 and see exactly what that value is doing and how it impacts our sim. Because in our simulation it starts off very fast and then it goes into slow motion. We start off with a high number of substeps. Let's turn our brain on. And you can see the substeps come down after frame 15, as does our time scale. And this just means that, once we have fast moving fluids or fast moving anything in Houdini, you want to increase the substeps so we can capture all that detail. And then once it slows down, we don't need too many of the substeps. So if we take a look here, we can see we're animating that here, and we're animating this with this fit. I think I showed this earlier. So this is basically just looking at our frames, and on frame 10 we're going to have a value of 3, and then on frame 15 we're going to have a value of 1. And this is for our minimum and this is for our maximum. So obviously we want a lower value for our minimum and a higher for our maximum. So we can see that that's going to be printed to our flip book, and we can do some comparisons. And talking of comparisons, I have a bunch here. So let's take a look at this one last. So let's start with this one. T amount. So here we can see our vorticity is in fact on, and we've got a value of 0.1. Here we have a value of 0.2. Here we have a value of 0.5. And here we have a value of 1. And if we can compare this, in this case, we don't really see a big difference. But I would normally run these these wedges, and then once you get to the end, come back and iterate over it again. It's a bit like tuning an instrument. You sort of start with your first string, and then you get to the last, and then you go back to your first string and repeat the process. And hopefully that second process is just going to be fine tuning, and you don't have to do too much work that second time round. But for the initial one, we're just going to pick something. So in this case, I think we're just going to keep. So in this case, I think we're just going to keep a value of 0.1, which is our default here. Next up, we can take a look at the splashy kernel versus swirly. So if we come over to, we want to make sure that we're not reseeding. We want the same amount of particles, so let's make sure that we turn that off. We can tick on vorticity. So in the vorticity here, we can see we have just a value of 0.1. And like I said, this, we're not really seeing this affect anything. I think this is just an attribute that we can use. You can use this for shading, or we could use this down the line, but it's not affecting our simulation currently. Next up is splashy kernel. So let's take a look for that. And you can see here we've got splashy or swirly. and for the simulation we want a splash. The velocity smoothing, we're going to leave that as a default of 1, but if you want to take a look at how that affects our sim, we can see here. Here we have a value of 0.1, here we have a value of 0.2, here we have a value of 0.5, and here we have a value of 1. So this is really smoothing out our shapes compared to a lower value like that. So you can see exactly what that's doing. But in this case, we're going to smooth out our shapes in many ways here. So we're going to go with this default one here. Next up, let's take a look at viscosity. And this is, how they say blood is thicker than water, and that's what they really mean is blood has a higher viscosity value than water. So you can see how with a high viscosity how thick this is, almost like mud or slime, whereas this one is more like a thin liquid. So if we come over to our solver, we enable viscosity, enable their attribute, it's called viscosity, and then you can just play with this value. I'm not so sure what the final settings were. We'll investigate that at the end, but for now let's just leave it with a value of 1, and like I said, you can increase or decrease this value. Actually, let's make it 0.1 for now. And next we have this slip-on collisions. And if we take a look here with a high value, you can see it's sort of slipping along the surface of our collision, wrapping around here and then dropping off. Almost like raindrops curling around the bonnet of a car, curling out underneath and then dropping off. So this is obviously a very high value. And we can just see how that affects our sim. And we're going to go with a value of 0.5, something like this. This is a bit too strong, and on these versions I'm not really seeing much of that behavior, but you can see here how it's just wrapping around a bit and then dropping down. So 0.5 is a good value. So let's increase that. Let's save so far. Next up, we have surface tension, and surface tension is kind of how, if you place a leaf on the top of water and it sort of floats on top, that's due to the surface tension. It's almost kind of like an outer skin on the water, just holding the fluid together. So obviously this is a very high value. Surface tension of 10. This is a surface value of 0.5, 0.1, and this is a mistake, but I believe this is a very low value. I believe this is actually almost close to 0.025. Sorry about that. I don't know why this didn't update, but it's clear that this is a much lower surface tension than 10. Oh, this is in fact off. Yeah, that's what that is. So this is no surface tension whatsoever. And on our final one, we actually had a very low surface tension. So let's go find that value. It's over here. Enable this. Believe it or not, it was 0.0025. And we're going to add another micro solver to control things. And you'll see how that affects the sim later. Next up, we have the stick-on collisions. You can see this is obviously way too high. This looks like it's sticking on the boundaries even. So So let's try a very low value of 0.01. I think I need to run these wedges again because we're not seeing the value. Let me open the final file. One thing I forgot to mention is if we come over to behavior over here, we're going to want to enable IDs and age. These are just attributes that we're going to use later. Do ensure that reseeding is turned off. Reseeding basically means that it spawns more particles, and we certainly don't want that. We want to start off with a fixed amount of points and have those points run throughout our simulation. And because we're not reseeding and we have this ID attribute, we can actually transfer UVs onto our particles based on the ID. So like sort of link the ID to a UV, and we could have UVs on our flip sim. So make sure that you have those enabled. Nothing here. There's vorticity. That is all correct. And back to our volume motion. This is all correct. This viscosity scale is actually a value of 1. Sorry about that. Surface tension. We want to enable our surface tension. And this is a value of 0.0025. We can take a look at that here. So we're just using a very small amount. You can see here the surface tension is off. Surface tension of 10. A surface tension of 0.15 and 0.15, and we actually just having even less than any of this. We're just having a tiny touch. And we want to enable the slip-on collisions, and under solver we're going to increase this to 6 so we can see what that does here. You can see this should be it. This is a very high value, I think, of like 10. I don't know why the info wasn't printed, but this was way too high. But you can now see exactly what it's doing, and we're going to have a value of 6. So something like this. Let's put the spectral scale 0.5. I don't have a wedge for this, but this is the settings in the final simulation. And I think this is a good place to save, and let's just run a wedge to see where we're at. Okay, so this is our result, and we're heading in the right direction, and we want to get this fluid to sort of pull and collect and stick to the surface a bit more, and that's actually coming from an extra microsolver that we adding to our DOP network. So we'll take a look at that next. So I've just come over to my simulation, and I have enabled cache here, so I can just do this in the viewport. Let's have a look here, and you'll see that there's kind of a link between this spectral scale and our surface tension. So, you know, with the surface tension on and the spectral scale of 0.5, you can see we're just going to get this very blobby behavior. If we were to turn off the surface tension, we no longer have that. And if I enable this and I come over to a solver and I increase this to 1, you can see this also will solve that blobby behavior. But we do want some of the blobby behaviors. Let's see what this does. Make it 0.1. 2. And you can of course come and experiment with this, but in our final scene, actually we did have a very low value of 0.5 and our surface tension was very low. Something like that. And the last thing we had was we put down a merge, and I'm just going to copy it from our previous file, this gas temperature update. And we have an expression on here, so this is going to multiply this down between frames 10 and 20 to 1.3 and then 0.8. So you can see here this is going to scale down. And if we want to enable our information on our viewport, we can enable this. Let's just round off our tank size so that we don't get this overlap. Let's just say 2, 2, 3. Let's actually make this 3 as well for now. And let's lower this. Cool, let's save. And you can see we've got this cooling because we do have a temperature on our particles. So we're going to be changing the temperature and the temperature to the viscosity. So this is going to change our viscosity value. And let's take a look. You can see we're getting this nice sheeting, we're getting this nice tendrils. And all we really need to do now is increase our particle count. And you can see how this is like cooling. You can see how this viscosity is now cooling down and we sticking to our face. So this is basically our final setup. The only thing that is different is where our points are being emitted from, and I will share this file and the final scene in case I missed anything, but you can see the effect here. So let's just save this, and for our final sim, let's increase our resolution and let's increase this to 0.75. Come back out here and let's save this to disk. Okay, cool. So this is our final sim that we did together, and this was the original file. And you can see the only real difference is the position of our emission, our source. So I'll show both of these files, and you can explore it, and of course run your own wedges, investigate these settings. I just think that's the best way exploring what a setting does really. It's just by messing around and taking a look. So we're gonna jump into the final scene now. We're gonna use this project file, and there's a few more things added, like some UVs, putting some color on our simulation, and the meshing. So let's jump back into Houdini. So we're in this final file here, and as you can see, the only thing that's really different is we've got our emission points. This is the original placing of them, so that's slightly different to what we had, but everything else is essentially the same. Our collisions and our simulation takes place here, gets cached out. Here we're just isolating the points. You can see we're selecting everything but the surface, because what we get out of here is a surface field and particles. So we just want the points. From here we're just going to put down a group delete to clean up our groups, and we're going to delete all the attributes that we don't need. So we're deleting everything except for these, and from there we're going to put down a null. And then this visualization is just like that visualization we created in an attribute VOP, where we're computing the length of the velocity. So if we take a look at this visualizer does exactly that. It's computing the length of the velocity, computing the length, and it's fitting it between 0 and 5, and then it's mapping it to this color. So we did the exact same thing in the previous file with a attribute VOP, but this visualizer does it for us. And from here, what we're going to do is we're going to freeze frame our simulation on frame 60, and that's just because on frame 60 we can see our splash is pretty big, and what we want to do is we want to project UVs onto this. And so we're going to use this UV project, and we're projecting down onto our surface like this. And in order to visualize that, we can use this point VOP, and we can project the UVs to color. So if we come to frame 60, you can see this is kind of how our UVs are being shot down onto our points. And because our points are not receding, our simulation isn't receding, each point has an ID, and that you know, that point number or that point ID isn't changing. If we had receding on, this wouldn't work because we would be receding points. So, you know, but because we have a fixed amount of points, we can map the ID to the UVs, and then we can just copy those UVs onto our points. So that's what we've got here. So yeah, freeze frame, project the UVs, copy those UVs onto our points. Here we're just visualizing that. Here we have we're not actually using this. There was some stuff here for creating a shader mask, but we're not using it. But essentially, we're coming back here, and we're creating some color. So you can, I think this is what we ended up using. We didn't end up using the UV part, but I will explain that. Here this is what we used. We just used some color variation. So if we dive in here, this is not being used, and I believe we're actually just using one of these. We're not using all of them, but we're importing the rest. We've got a constant value, and we're adding that, and we're creating a turbulent noise, and we're fitting that, and then we're exporting that as mask, and here you can see it as color. So we're creating this mask 1. Let's see which one we've actually using here. Well, I'm going to show all of them. So you can see we've just got some variation. And of course we can change the frequency of our noise. Let's copy parameter, paste reference, paste. You get the idea. We can just get some variation on our simulation. I think this was 2 point something. And here we have this to create our mesh. So this particle surface fluid node is just going to create our mesh for us. This may take some time. So you can see our mesh. And let's investigate our settings. Our particle separation is, you know, that original simulation that we used. So this is the same particle separation as our sim. Voxel scale. We're eroding it a bit, and we're transferring some attributes. But this is pretty standard meshing stuff. And we're transferring that color on those different masks, those different color attributes, back onto this mesh. So now you can see we've got that color on our mesh. And here we're transferring the UVs, and I've cached this out so I can show the UVs a little bit better down here. Here we just multiplying our velocity down. That's just for the motion blur. And this is just because, you know, it's a slow motion effect, so we need to You know, if our time scale is 0.2, we need to multiply our velocity down by 0.2. So here is our mesh. I've just cached this out to disk, and here I just wanted to show the UVs because it's a bit difficult to see with that color. So I'm just deleting that color briefly, and as you can see, we've now got these cool UVs on our mesh. Here we can put an image on. Let's put this after our color delete. Yeah, you can map any texture you want to this and it's going to be stable. So if I run a flip book, let's just do that now. You'll see that we've got stable UV. So I'm just going to let this run for a bit. So as you can see, we now have these UVs and they are mapped to our liquid simulation. And you can see at frame 60, I think it was, our UVs are pretty much spot on, and then they sort of liquefy before and after. So they shrink before 60 and they expand after 60. And of course we can then, you know, apply a texture to this. So that's it for the simulation and meshing part. Thanks for watching. See ya.